In this presentation, we will look at some exercises from section 1.2 that deal with direction fields and separable differential equations and some of the connections between those. The first exercise, we have a differential equation which is given in standard form. Anything that's given in that form is a differential equation in standard form, and the basic idea with direction fields is we're solving the problem geometrically. We're not going to be able to find the solution exactly, but we will have a pretty good idea of the behavior of the solution with this method. Especially, we'll have a good idea most of the time of the long-term time behavior of our solution, in this case of the function y. Our given differential equation is y prime equals x plus y. So if we think about the meaning of that geometrically, that means the slope, which is y prime, has a value k on each of the curves x plus y equals k. Those curves are called isoclines for constant direction. Solving the isocline for y, just for the convenience of plotting, we have the slope of the solution y prime has a constant value k on each of the curves y equals minus x plus k. So in this problem, our isoclines are lines with slope -1 and variable y-intercept. And so plugging in a few values of k to get an idea for how this solution behaves, y prime is equal to 2 on that isocline, y prime is equal to 1 on that isocline, y prime is equal to 0 on that isocline, which means our solution trajectory is flat as it crosses the line y equals -x, -1 on that isocline, and -2 on that isocline. So in this graph, at the top of page 2 of this presentation, I've plotted my 5 isoclines that I found, and then I sketched in small segments which represent portions of the solution trajectory as they pass across each of those isoclines. In the directions, I asked you to sketch at least 3 solution curves, and in this case I sketched 4 solution trajectories just by following the direction suggested by those isoclines. Now in exercise 2D, we have a first order differential equation. It's fairly easy to find the exact solution of that initial value problem just by integrating. So there's the exact solution. It's interesting to see here that the exact solution agrees with the direction fields method. So the time derivative of p is -2 on t equals 1/3. So that would be this vertical line, and then similarly all of my other isoclines are these vertical lines, and the slope of my solution has the indicated value on each of those lines, and I drew the trajectory that passes through the initial value p of 0 equals 1, and it looks like that graph agrees with the exact solution. In exercise 3A, we have a separable differential equation where the variables are already separated, so we go ahead and solve by integrating and doing some easy integration. Actually, there's a typo on this one. I'm not going to go back and do it over again, but when you anti-differentiate the right-hand side, you should get the constant. It would be the antiderivative of the right-hand side instead of 0. So this equation right here is your solution, except the right-hand side should be 0. I'm sorry, the right-hand side right here, maybe I'll just cross that out. I guess maybe I can do that and try to put in C. That didn't come out very well, but hopefully you follow that. When we anti-differentiate the right-hand side, the antiderivative of 0 is a constant. Now, in this problem, our dependent variable is p, so we want to solve for p if it's relatively easy or convenient to do that, but it's not really a simple matter to solve this since it's a cubic is a function of p. So we'll just leave the solution in that form. That's the general solution in implicit form. And that's as far as we would go, since it's not very easy or convenient to solve that for p, which is our unknown function, our dependent variable. In part F, we again have a first order differential equation given in differential form. Initially, the variables are not separated, but with a little bit of rearranging, we have our variables separated here. So then we go ahead and integrate, and we have two easy integrals that we do by substitution. U equals t plus 4 in the first integral, u equals p minus 1 in the second integral. This time I correctly anti-differentiated the right-hand side and got a constant. That gives us this expression. At this point we have our solution in implicit form, which is how we left it in part E. But we're going to go ahead and solve this using properties of exponents and logarithms, which are similar to other things that we've been doing with our other separable DEs so far. So since we have natural logs on the left-hand side, we exponentiate both sides. In this step here, e to a constant is a constant, so we've redefined the constant at that point. We use a property of exponents here to break up the two factors on the left-hand side, and then we just have the absolute value of t plus 4 and the absolute value of p minus 1. And at this point we can drop the absolute values, because by dropping them at worst we're off by a factor of -1, so that factor can go into this constant c. So if you like, we've redefined the constant c again. And at that point we basically have our solution, but we want to solve it for p if it's easy or convenient to do that. So just dividing both sides by t plus 4 and then solving for p, we have our general solution in explicit form. P is 1 plus c over t plus 4. In the next exercise, exercise 8c, we are given a first order differential equation with time as the independent variable. We have one equilibrium point at y equals 1. That's the only value that makes the right-hand side equal to 0. And we want to investigate the stability of that equilibrium point. And if y is greater than 1, looking at this differential equation at the right-hand side, it's easy to see that the derivative would be less than 0 in that case, which makes your solution decrease, the upper part of our graph. If y is less than 1, on the other hand, again looking at the differential equation at the right hand side, that's going to make the derivative positive, which will make our solution increase. So either way, our solution is we can see, even without solving the equation, our solution must approach the equilibrium at y equals 1. So we call that a stable equilibrium point. And you should try and find the exact solution yourself of that separable differential equation and make sure that the exact solution agrees with what we just concluded based on the equilibrium and stability. In part F, we have a first order nonlinear differential equation with two equilibrium points at y equals 0 and y equals 4. And if we analyze the stability of each of those, again looking at the side of the differential equation of the right hand side in various cases depending on where y is, if y is greater than 4, the derivative is going to be positive, which makes our solution makes the solution grow. If y is between 0 and 4, the function will decrease, and less than 0 it will increase. So that gives us an unstable equilibrium at y equals 4 and a stable equilibrium at y equals 0. So if our initial condition is y of 0 equals 1, which is in between 0 and 4, then our solution function we know will approach 0 as t approaches infinity. And it's a good idea to compare this again to the exact solution. It is a separable differential equation, so you can find the general solution exactly of this differential equation. You'll need to use partial fractions for the y integration. If you need help, look on the next page.